So let's do today's Leetcode challenge. Today's 27th Jan 2022. And I'll just quickly share my screen. Actually, today's problem is something which I've seen before, so I have a little bit idea, but it's quite a while. So let's see. We have to find maximums of two numbers. Okay, so you are given an array here of integers, and you have to find the maximum result which will be possible for x number of i's or number of j. So take two elements out of this, find maximum, and then check whether it's the maximum or not. Let's quickly look at the limits. So the number's length would be less than 10 raised to 5, which means that order of n square might not work. We need to find a solution either in order of n or order of n log n. So let's see if what would be the brute force solution. If we are given a number, a list of numbers, then we just take two numbers from it and try to see whether it forms it's a maximum or not. And where it's just that we just do 3 with 5, 3 with 10 or then 3 with 5 or then 3 with 25 or then 3 with 2 or then 2 with 8, and then see which one is maximum. Similarly, do 10 with 5 and also on and so forth. So this would be an order of n square solution, but we want something lesser. So for that, let's just see what the observe what the property is. So zeros or 0 would be 0. Then ones or 0 or 1 would also be 0. Then zeros or 1 would be actually 1. And again, ones or 0 is 1. Apologies for this very bad handwriting. I don't have anything good right now. So yeah, we have these things, and now we want to find the maximum. So the maximum cases are like either 0 is XORed with 1 or 1 is XORed with 0. We don't want the same digits to be XORed with each other. We want the digits should be different. And another property, so this is the first property. And the second property is like any integer is stored as a 31 bit, like 32-bit number. That is, it goes from like say 0 to 1, 2. So there are like about 32 bits total, 31 bits. It's indexed at 0. And to know that whether a number is maximum or not, just tell me like this number is bigger 101 or this number is bigger 100. Yeah, this number is 5. Yeah, and this is 1. So of course 5 is bigger. How did we know that? Because the most significant bit has a 1 in it. So here also we would try to get like a greedy way of getting the most significant bit that we can get 1, like push 1 towards here as much as possible, and then here could be a 0. That would be also, of course, a bigger one. So here we are trying to solve it via a try approach, where what it means is if you are aware of the basic data structure called try, you build a node and then you have its children below it with the same structure, and wherever there is a filled position, you insert the node at it, and then if not, then you just revert it, keep it as null. So here, for example, we have 3, 10. So 3 would be like 0, 1, 1. And since we are going from most significant bit to least significant bit, we'll start. We have to find the answer in the first step is this. So we'll try to put it like this. So here all would be zeros. So then you have a try root. This is the root of the try. And it will have just 2 elements, 0 or 1. And if it's 0, then it goes, say, on the left. And if it's 1, then say it goes on the right. sense? It's like a binary tree right now. It's not a long try that you would imagine for 26 characters of English alphabets. So say here it's a root, and then you have to like 4 0 0 0 like this for say 20, 30, 28 times, and then 29 would be again 0, and then 30 and 31 would be 1. Okay, I think there is something wrong that I've communicated. So in fact, we're going from down to up. So the 0 and 1 would be 1. First 3 is consisted of this. And then 2 to 31 would be zeros. But you get the idea. So we're looking from here. Let's take another example, 10, which is 8. Then 0 for 4, 1, 0. So this is 0 bit, 1 bit. And then till here we have the 31st bit. So similarly, here also it will be 0, which is the same here. 0, 0, 0. And here at the 28 bit, we have a 1. In 29, this is 2 and 3, which would be 20. Like counting from here, it would be 28 bits of 0. 28 bit would be 1. 28 bit would be 1. 29th would be a 0 again. 1 has a child 0. Then 30th would be again 1, which goes on the right. And then on the left 0. To get the idea, right? We build this tree, and now when searching from the tree, we see whether if there is a 0 encountered and whether there is a corresponding 1 encountered in our nodes. If it's there, then the XOR of 0 and 1, as we saw over here, would be 1. So this answer would be, of course, better than any other number. So you select the numbers either from the one which has 0 inside it and the one that has 1 inside it. Okay, so let's go to the coding and see how it goes. Find maximum of XOR. So first we'll create something like we'll add numbers to a try. So we'll first create a try. We add our numbers. And the try would have two childs. Try left for 0 for a 1. And then we have just basic structure where left equal to null. Oops. Here we are not even keeping a leaf node, which we generally keep in a try, because we know that all of them are of a fixed length 31. So there is no difference in the length or the heights of the different integers. All ends at 32. So now for here we'll just create a root node of try. And then for integer n, all integers in the number, we'll say build try n divided the root. So we create root try from any number divided root. Here we'll now here as we saw, we'll start from the rightmost thing and then go towards the left, and wherever there is a 0 we'll put left pointer yes, and wherever there is 1 we'll put the right pointer yes. Okay, so because this is a shallow copy, we are okay to modify the root, otherwise we would have to create a new variable and assign it to root, but we are okay with this. So now here we'll do like for equal to, we want to push forward like 30. 31 bits. And we'll create a mask. Which is one which is pushed back 31 times, like the I times. And then the bit would be the number multiple, the number and mask. So that would be like if it's 0 then 0 and 1 then 1, and the rest all would be zeros. Make sense? Now we see that if it equal to 0, then dot left equal to 5. Yeah. And then root is root dot left. Makes sense? So if it's left, we go create a new try there and then make also the root till here. And if it's right, if it's 1, then we go to the right and also create the root. So build the entire tree in that way. And then the second iteration, it will go to the 30th bit, which would be this. 30th bit, then 29 bit, as much as it will go till the last bit. And then put the 0 and 1. Okay, so till here our try is built. Now we have to find the maximum one. On the root. We get the result back. From the try root. So here now what we'll do is we'll check like for each bit we have a 0 or 1. How will we do this? So whether if we have a 0 and 1 both, then how will we decide which child to go to? So I think once we have pre-computed, we have to find the maximum possible try for root and also for a particular number. And also call this all the time. We are going through this and then the 32 bits, all numbers in 32 bits. Added. Okay. So now each number we are trying to check whether its counterpart, which would make a maximum possible thing, it's present or not. If it's present, then what is maximum one available? Which means here we just check. So we have to extract the bit, the last bit of here as we did over here. So yeah, let's go. Same, we extract the bit. Equal to 0. Then we say that fruits left child exists because it's 0, it's already on the left. So to make it 1, we need a one counterpart, right? So we just need to first check it for the right side. If root dot right is not equal to null, if there is a present, then the right part to go is root dot right. Not, then you have no option but actually to go to the root dot left. Makes sense? Because the bit is 0 at that time, to make it maximum, you need one counterpart, and for one you have to go to right if it's available. There is a number which actually makes it the maximum with one at that position, and if not, then you go left. Similarly, if the current bit is 1, then you check in the opposite way. So current it's 1, so you go to 0 if possible. Not, you go to the right. And you put for every other bit like this. Simultaneously, you also need to track. So you need something called result. So initialize at 0. And initially, and you go to the right. So we can just modify the here itself. You can have result is nothing but results or now because we have a 1 here, it's going to the right side. We just make 1 pushed 8 times and just sort it with result, so that the result will also have 1 at the effect. With 0, we don't need to push anything. Similarly here, if it's going to the right, make result is also right, and then at the end just return the result, which is the maximum possible counterpart available. If you know, now let's see trans. Okay, the answer is wrong. Let's try to debug. Let's see whether it's building the right try or not. See, this is giving us the correct one. So the next time we make the key smaller just to check easily. So 3 we have a couple zeros. And the last 2 is, oh, it's coming a bit. And then it's 0. So for the last which go to right, and for the 5, sorry. 1 and 3 and 1. Yeah, makes sense. But this is correct. And then we have 3, 10. We're getting 10 as output. Now for each number, we have to see Let me just check my previous submission, which was like 1. So I've just forgotten it is. I think I'm missing some part of it. This is right. So here I think I've taken left for 0 and right for 1. Whenever it goes right, we're doing this. Oops, yeah, sorry. Mistake. So whenever we have a 1 over here, we just need a 0, we go back to the 0, and then we XOR here. Oh, it was such a silly mistake. So this is not working. Still something just wrong. This is root. Build a structure. Right. Maximum possibility of maximum. So here we are pushing it to right and then ending with 1. Oh, yeah, this is the catch. So what happened is here, what we're doing is we push the mask bit inside. So then even if it's like 0, it's going to have 1 somewhere on the right? And that's when it would be 0. Does it matter really? So let's select this for the bit instead. Leave by I with 1. Last bit. Oh, I think we are overriding every time. So I'm new things. So we just build a new thread if that is null. Okay, so before that we were just overriding it, and whatever number we had previously, we were losing it. So in fact, only the last number was staying in our bit, but there are different now. There are different bits, and now it works. So you can just comment out this is out statements. So this is an order of n squared solution. Order of n solution. Wow, and it's lesser than the previous, which is like 95%. Great. Thanks. Let's see tomorrow the next part.